All right, so this morning we'll be looking at exponential growth and decay problems, which are just applications of differential equations. All right. All right, so all right. When you're dealing with exponential growth and decay, 99 times out of 100, the problems that you're dealing with are problems that deal with an extrinsic property. An extrinsic property is a property that is determined by the amount of substance that you have. Okay, so your growth rate is usually proportional to the amount of stuff that you have. So if you're thinking about things in a differential equation sort of way, that lends itself to saying that the rate of growth is proportional to the amount of stuff that's there. Okay. And we've solved this differential equation before. All right, so that's just the pure math of it. But let's actually look and see what these terms were, and let's define these variables so we can recognize what we're dealing with. All right, so going back to the original problem itself, when you dealt with things that were proportional, you had a constant of proportionality, okay? This constant of proportionality is a constant that is related to the substance or the item or whatever it is that you're talking about. So if we're talking about like the growth rate of rabbits, this is a number that's associated with how fast a rabbit can breed. Okay, like the gestation period of a rabbit. Okay, or if you're talking about the decay of some isotope. Okay, this constant is something that's related to that specific isotope. Okay, it's something that is an intrinsic property. It's a property specific to the material. Okay, or specific to the species or whatever that is. Yeah. So so K is a constant that has to do with whatever thing it is you're dealing with. Okay, not so much how much of it you're dealing with it, but like, for example, it could be the rate of the bank account. You know, it's specific to the bank account. Okay? All right. Not so much how much money is in the bank account, but what the rate is for that company. Now, let's go back into here. We have this. Now, that B term came from this constant. Okay? So let's think about this for a second. We have some constant times an amount plus another constant. So what we've basically got here is a line, y equals mx plus b. And now granted it's the natural log of the absolute value of y, but what I'm talking about here is a linear function, okay? And if we were to graph something like that, it would look probably generally something like that, where k is the slope and c is the y-intercept. So for a second, let's say to ourselves, all right, c is a y-intercept. What do we know about y-intercepts? What do we know about y-intercepts?
X is 0.
Say it again?
X is 0.
When the x is 0, when you're talking about none of the stuff, okay? It's kind of like where you begin. Now, if x was time, okay, so we're talking about how time progresses and how things change over time, which is pretty common. This would represent the amount of stuff, whether it be money or rabbits or isotopes at time 0. So it's your initial starting amount, okay? So this constant b is your initial amount. Okay? And that e is related to the growth of the species. Now, for a second, I'm going to take a step away and kind of remind ourselves what the heck E is, because it's been a little while, and it's one of those things that we just kind of often just say, okay, I believe you, Ronco, E's a number, moving on, and we use it all the time. But we don't really dive into what it is, okay? So for a moment, we're going to take a step away, but before we do that step away, I want to throw at you that this is something we've seen before. So this y right here, we could say this is the final amount. And x, this is my independent variable. X is very often time, or steps, or, you know, a number of applications of something. So this is progression, usually time, or some other progression. It's your independent variable, okay? And like I said, k is the constant of proportionality, which is related to how much things change. So we've seen this thing before. And when we saw it when we were dealing with interest. Okay? So going back to the interest formula, the amount final is equal to the amount initial times 1 plus your rate all over the number of times you compound, the number of times you compound times time. Okay? This is a formula that we've used before. We've talked about it before. You've dealt with it in Algebra 2 a lot. And this is a formula that happens all the time. Okay? So it's one of the ones that we might want to just put in our brains. All right. Now, you might have learned, hopefully, somewhere along the line, that if you compound more often, you get a better result. Okay? You usually make a little bit more money. Okay? And compounding is generally good. All right? So, now I'm going to throw a hypothetical scenario at you. I own a bank, and you have $1,000 that you want to deposit in the bank. And I say to you, guess what? I'm really, really nice. I'm going to give you 100% interest. Not bad. Deposit your $1,000 on January 1, roll back the next January 1, boom, you got $2,000. Not bad, right? That's good. Okay. So now that means that my rate is going to be what? If it's 100% interest, what's my rate? 1. Okay. All right. So now if I did that, I would say now I'm going to sweeten the pot. And instead of compounding once a year, I'm going to compound twice a year. Okay? So now n is equal to 2. So just to do the math real fast, put up a calculator. Remnants from Algebra 1. All right. If I'm going to deposit $1,000 in a bank account with 100% return, and I compound twice a year. Okay, and time is 1 year. I'm going to let it go for a full year, so t is 1. Yep. I'll make a little bit more than double my money. Whereas just straight up compounding it one time only gave me 2,000, right? Are we cool? So now let's go back and say, you know what? I'm going to be really nice. I'm going to compound every month. Nice. You went from $2,000 to $2,250, all the way up to $2,600 and some change. Pretty good. What if I compounded every day? Even better. And let's include leap year. All right. All right. This is a quarter of a year. Oops. Oh, the 1 plus. Whoops. Thank you. Whoops. $2,700. Okay. What's that? Well, you're still getting 100% return. But what's happening is, let's go back to the month example. It's a little easier than the day example. I'm taking your rate of 100% and I'm dividing it by 12. So you're not really getting the full 100% each time. You're only getting that amount of times interest. But what's happening is that once I give you that money gains interest for the next month. You see? So the more I shorten the interval, if I'm going down to a day now, if I compound your interest, let's just say you have that $1,000 January 1. I compound on January 2nd. Okay? I'm going to give you the interest of 1/365th, okay, of your money. Well, that 38 cents, or whatever it is, okay, you're going to use to build interest for the rest of the year. And then on the second day, you have $1,000.38, and I'm going to take the interest on that. So you see, your rate is small for each day, but because you get the money, you're given the money more often, you can reinvest that money more frequently. And that means you're building more. You're building on your money more often. Okay, so it's one of those reasons why, like, all right, now this is just a little side note. You know, all these you hear about all these corporations that get into big trouble and they get sued and they wind up like having judgments of billions of dollars. And what do? They drag it out for years and years and years and years before they actually pay it off. Well, why are they doing that? Well, they're doing that because they're investing that money. And then by the time they give that money away, they've made several $billion off of it on interest alone. So holding on to your money longer means that you're going to make more money off of it. Okay? It's kind of dirty, but because you would think, well, what the heck, man? They got to pay the $10 billion anyway. Just pay it now. Well, if they hold on to it for 10 years, that $10 billion is now $12 billion. Sure, give that $10 billion away. They made $2 billion on it. And believe me, lawyers don't cost that much. So it's cheaper to hold it off in court longer and longer and longer. Anyway, enough of corporate legal stuff. So what's happening is, now let's look at this for a moment. We went in and we first did it for half a year and we made $250. That's a big jump. Okay, $250 was a lot. And then we went to a month and the difference was only like $400. Okay? So we went from once to twice to 12. And then we went all the way to 365. And notice, we didn't gain a heck of a lot by going from month, $2,613, to a year, $2,714. So it's almost kind of like the law of diminishing returns. Yeah, they got a little bit more money, but not a heck of a lot of money, you know? So what if we were to compound every second? It would make a little bit more money, but not a heck of a lot, okay? And what's happening is that we're creeping up on a value. And that value is E. It's, notice, 2,714, 2718. And what's happening is that if we take this function, going back to the math, we take this and take a limit as n approaches infinity for 1 plus 1 over n to the n, okay? And we compound all the time. What happens is that this goes, actually I'll just put a t here, e to the t. We approach the function of e to the t. You see? It's neat. So this is where e comes from. It comes from growth. Okay? It's the maximum growth that you're going to get provided that you reproduce all the time and you get 100% on yourself. Okay? Now anything less than 100%, like let's just say, you know that they say like you hear these statistics like the model American family has 2.4 kids, right? Well, obviously there's not 0.4 of a kid, but there is some, for every 10 families there will be, 4 that have 3 kids and 6 that have 2 kids, okay, or some distribution thereof, you see? And the average comes out to be 2.4. Well, that number actually is dropping. Okay, and it's actually, in some countries it's below 2. And in that situation where 2 adults are only producing 1 kid, you're getting a negative population growth. It's actually going down, okay, because the same number of people, 100 people are not producing 100 babies. They're producing maybe 90 babies or something like that. So if you keep doing that over time, we have a problem. You see what I mean? Okay. So what I'm talking about here is that we can model growth using the exponential function because the exponential function is a continuous function. It's a smooth curve, okay? Whereas if I was doing compounded interest and I was talking about per month or things like that, it would look like a step function. You would have this much money up until the end of the month, and then it would go up, and then you have this much money, and then it goes up, and then you have this much money, and then it goes up. It would look like a stepwise function at each first of the month, it would jump, you see? Whereas if we're continuously compounding, it becomes a smooth, nice curve. All right? So this is why we care about E, and this is where it comes into play. So going back to where we were, the differential equation piece, if I were to take this function and take a limit as n approaches infinity, I wind up with amount final is equal to amount initial e to the kt. Whoops, excuse me. Which is the same thing as we saw in the last slide. Y is equal to some number, which is the initial amount, e to the kt. Okay? So this is where exponential growth and decay formulas come from. It's not magic, it's math. Okay? Now, depending upon the problem, some information will be given, some information will not. So, let's go through some of the examples that are in here. Okay. Number 1. Population of a country is growing at a rate proportional to its population, so that means we've got y prime is equal to ky. Okay, so let's look at that for example. Growth, speed of population change, is proportional to the population. Okay? It's not proportional to the year. It's proportional to the population. The more that you have, the quicker you grow. I mean, think about it. You have a desert island with 2 people on it. The population will grow, but it will grow very slowly. It might take you 100 years before you have 3 generations, before the population doubles. And then you probably have like weird birth defects. But moving on. So, yes, I recorded that. Next, but if you have a slightly bigger island like New Zealand with a lot more people on it, the population is going to grow faster. See what I mean? Okay. If the population rate per year is 4% of the current population, how long will it take for the population to double? Okay, so this kind of a question, how long does it take for it to double? How long does it take for a triple? If we're doing a decay problem, how long does it take to get to halfway or a tenth or whatever the heck it is? These kinds of things pop up all the time. Now, for a second, before we even get into the second sentence, I want to talk about this one for a minute. The rate per year, so the rate is y prime, is equal to 4% of the current population. Okay? Now, for a moment, let's ask ourselves this important question. We need to make sure that we are keeping this number under control. We know what we're dealing with. If you put a 4 in there rather than a 0.04, that means you are taking you're going to say e to the 4th power rather than e to the 0.04 power, which means the sucker is going to grow really fast. We don't have people, we have rabbits. Okay? We might have rats. They grow that fast. Okay? Yeah. All right. Pretty fast. And we'll do some of those. All right. So if it takes time to double, well, doubling would mean that the amount initial and the amount final are equal to 2. The amount final is twice as much as the amount initial. That's what that's saying. Does that make sense? And it doesn't really matter how much we have. We could have a population of 1 million, we could have a population of 1,000. It doesn't matter. It's twice as much. And in fact, if we just threw a number at it and said, okay, I got 1 million people, that would be my B. That would be, and we're going to get to the equation in a minute, my amount initial would be 1 million, and then my next would be 2 million. And then when I divided it, I would get 2. That's the whole idea. So now, here we go. We have y prime is equal to some amount in, excuse me. We don't need to solve the equation. We already know what it is. Plugging in what we know, k is my constant of proportionality. And again, if you remember, k is something that is related to the species, right? And in this case, the species that we care about are humans in this group. So y is equal to b e to the 0.04 t. Now, we do not know what the initial population is. We do not know what the final population is, but we know what their ratio is. So going back, 2 is going to be e to the 0.04 t. Now, solving for t by using a natural logarithm, natural log of e is 1. And there you have it. And again, this is a calculator job. It's going to take 17.328 years. Now, again, when you're dealing with these things, it is important to keep track of the words that they ask the solution in. You know, for example, you know, if we're talking about the population of elephants in a jungle, you can't have 17.3 elephants. Okay, so you always have to ask your question: should I have 17 or should I have 18, or things like that? Okay, especially if you're talking about discrete units. Now, if we're talking about time, that's another thing. Okay, that's fine. We can say 17.3 years. That's not a problem. But if we're talking about discrete objects, please realize that going back to algebra, you know, math, middle school, you can't have 2.4 people. Okay, good, done. 17.3. Now remember, IB wants 3 decimal places of accuracy, so you would report this as 17.329. Okay? All right. Number 2. Bacteria in a certain culture increase continuously at a rate proportional to the number present. So that again tells me I'm dealing with y is equal to b e to the k t. Now here's where we're going to have, we don't know what k is. They didn't tell us that. They didn't give us a rate. But they did say if the number triples in 6 hours, how many are in 12 hours? Okay? So we have to find what k is. So we're going to use the information that we were given to find k, and then we're going to use that k to answer the question. Okay? So if it triples in 6 hours, that means y over b is equal to 3, and it happens in 6 hours. Okay? Taking t in hours. So natural log of 3 is equal to natural log of e to the 6k. Natural log of 3, 6k. K is equal to natural log of 3 all over 6. Whatever decimal that is, if you're on an IB exam, my advice would be to either A, store this as a variable in the calculator so that you can have all of its gory digits, okay? But don't ever round now. If you round now, you're going to have propagation of errors all throughout your problem. My advice almost would be to leave it in exact form if it's the exact form is that simple. Okay, if your exact form is really ugly looking and it's like some crazy arctangent with natural logs and 17th roots in it, then fine, leave it as a crazy decimal. But if it's something simple like that, you might as well leave it there. Okay? Now we're going to find out how many is in 12 hours. So y is equal, now we don't know what b is, but we know that y over b is going to be equal to e to the kt. We know what k is, so we can plug it in. And that's a calculator job. Oh, no, wait, 12 hours. Whoops, excuse me, t was 12. We got to plug in 12, too. Whoops. Now, that would make this times 2, right? Nine times as much. Now, for a moment, this should make sense. For every one thing, it triples in 6 hours. Okay? So let's see if we can visualize this graphically. I've got at t equals 0, I have one thing, right? What are we talking about? Bacteria. Okay. I've got one of bacteria. 3 hours goes by, that one glob turned into, oh, in 6 hours, it tripled, right? Okay, 6 hours, each guy triples. In 12 hours, this guy is going to triple, this guy is going to triple, and this guy is going to triple, leaving me 9 guys. 9 times my population, which is what we saw. Okay? So it should intuitively make some sense. Okay? Half-life. Number 3. Radium-226. Hey, what you got for me? Okay, thank you. Decay to the radium proportional present. Its half-life is 1612 years. So the half-life. Hey. Yeah. Yeah, sure. Half-life is 1,612 years. Okay. Now, that means that, yeah, definitely not a lot of fun. It takes a long time for it to decay. All right. So y is equal to b e to the k t. Okay? So what this is saying is that in 1,612 years, my ratio of stuff will be a half. Now again, I mentioned that k was a proportionality constant. It was something that was specific to the material. K is the half-life, okay? What number am I on? 3. Okay. So now, doing a little rearranging. All right. How long will it take for 1/4 of a given quantity of radium-226 to decay? So it's not asking for the entire half-life. It's looking for enough of a half-life so that only 1/4 of it is gone. Okay? So going back. And now, plugging in what we know, Now, at this point, there is some basic algebra, logarithmic algebra that will make your life a little easier. Realize what you have here. Okay? See how I solve for t? That's 4 to the negative 1 and 2 to the negative 1. So that gave me my negative signs, and then they canceled. Believe it or not, if you look carefully, you'll notice the natural log of 4 over the natural log of 2, that's the change of base formula. Oh wait, I have to be careful. I just noticed that I made a mistake. Do you see it? No. There's nothing wrong with my algebra. I've made a mistake. And it's in the wording of the problem. Read the question carefully. I'll read it again. How long will it take for 1/4 of a given quantity of radium-226 to decay? 1/4 decays. How much is left? 3/4, not a fourth. Right here, if you'll notice, by the way, this simplifies to 2, so it would be 2 half-lives. Natural log of 2 to 4, 2 of 4 is 2. So I would have 2 half-lives. What I've solved is, how long does it take for my initial amount to turn into my final amount? And my final amount is 1/4 of the original. That's not what the question asked for. The question wanted 1/4 to go away, leaving 3/4. So you have to be really careful sometimes in the reading of the word problem. It does, but that's okay. We'll live. And again, this is a calculator problem. So you're really all right from my point of view, if you were to just plug this sucker into a calculator and spit out a decimal. So if you want, you can do that. You don't have to solve it algebraically. Yeah, let's get some calculators on that. I don't know. Thanks. Questions like this, you get to an answer, you just plug that guy into the calculator, man. Is it dead? Is that calculator?
No, she's just being picky.
Oh, please. Will you put it on my desk?
Yeah.
Like 600 something years. Is that what you guys got? Why do you, I just showed you the syntax. All right. All right. Okay. So number 4 is very simple. I'm going to skip that one. All right, number 5. This is one that's a little bit more for those of you doing biology, archaeology, that kind of a thing. This is relevant. Okay, one important method of dating fossil remains is to determine what portion of carbon content of a fossil is the radioactive isotope carbon-14. During life, any organism exchanges carbon within its environment. Upon death, the circulation ceases, and the carbon-14 in the organism then decays at a rate proportional to the present. The proportionality factor is 0.02. Okay, so K is equal to 0.012% per year. When did an animal die if an archaeologist determines that only 25% of the original carbon-14% is still present in fossil remains? So Y over B is equal to 1/4 e to the 0.0. Now careful, watch, it's a percent. Okay? All right? And you guys can crunch this guy from there. You're going to notice an interesting result. I'm going to put it in the calculator. Yeah, what does your answer turn out to be? A negative number, right? And that makes sense because it's time ago. It's in the past. Other things, other times, sometimes depending upon who your teacher is, what your textbook is, or whatever, they'll say, "Oh, this is a decay problem, so I'm going to make my proportionality constant negative artificially." And what that would do is, now if we solve this problem, okay, and then you wind up with negative 11,552. Okay. But other textbooks, other teachers will, references, resources that you go out and find, will say, since this is a decay problem, we're going to modify our formula to be this guy. All right? Since it's decay. Well, that doesn't do me any real difference. What it does is when I rearrange it and if I were to plug it in and solve, this would be 1/4 e to the negative, and then when I solve, and I'm going to get the same number out of it, except that it's going to be a positive number, and now I just need to say it was that many years ago. But still, it's the same quantity. You just have to put it in its context. If it's decay, it'll go down. Same as that. Done with that. Okay? And finally, number 6. I'm going to leave this one to you. This is a fun problem. So in the last 10 minutes, I hope that we can get numbers 4 and number 6. For those people that are watching this video, I'm going to write number 6 on the board, and then we'll call it a day. This episode of the Ronco Show has been brought to you by Exponential Growth and Decay and the letter E.